Welcome to comp452, and today we are going to discuss flip-flops. So basically this is the second part of the lecture. In the first part we discussed latches. So what are flip-flops? Flip-flops are flip-flops. These are synchronous sequential circuits. Synchronous sequential circuits. Sequential means that these circuits, their output does not only depend upon the current inputs, but it also depends upon the sequence of past inputs. Or in other words, these circuits have memory elements and they have a state. Synchronous means that any change in the output, any change in output is synchronized. It's synchronized with an external signal, and that signal is almost always called clock signal. Okay. In contrast, latches are asynchronous sequential circuits, which means that the change in their output signal is not synchronized with any external signal source, and it only depends upon as soon as the input signals or the state of the circuit changes, the outputs also can change. It's not necessary that state changes result in output changes, but normally when the state of a circuit changes, there is a possibility that its output also changes. Okay, so now let's construct we constructed a D-type latch in the previous discussion. So now let's construct a D-type flip-flop. To construct D-type flip-flop, we will use a pair of D-type latches with control input. So let's quickly review the circuit symbol of a latch with control input. So this was D input, this was control input, this was control input, then here we have Q output, and here we have inverted Q output. So this is the circuit symbol of a D latch. So we are going to use two of these latches to construct our flip-flop. Okay, so let's construct our flip-flop. As a matter of fact, let's connect our next latch, or cascade the next latch like this. So this is D input of the next latch, this is control input of the next latch, This is Q output of the next latch, and this is the inverted output of the first latch, of the second latch. So normally what we do is we say that this is our master latch, and this is our slave latch. This is master and this is slave. Okay. So let's connect this output. So the output of master latch is connected to the input of slave latch, or the output of master latch is connected to the D input of slave latch. And we will not be worried about this inverted output, and we will say that the external signal that we feed to this latch is D, and then here we connect our CLK, which is clock signal, and this clock signal, after passing through an inverter, a NOT gate, it connects to the control input of second or slave latch. So the clock input goes directly to the master latch, and it goes to the let me repeat, the clock input goes directly to the control input of master latch, but it goes through an inverter to the control input of slave latch. Now this whole assembly is what we call our flip-flop. Okay. Now let's analyze this circuit. Okay. Now let's assume that this CLK, or let's write it here, CLK, at CLK input we give this signal. So this is a sort of square pulse, and this is logic 0 and this is logic 1, or low voltage and high voltage. Okay. So let's assume that we are at this point. We are at this point where CLK input is 1, where CLK input is 1. Okay. So this means that this input is 1 and this is 0. This further means that master latch is enabled, but slave latch is disabled. Okay. So this further means that input of master latch goes to its output, but the input of input of slave latch cannot reach its output. Okay, so let's imagine for a moment that which color should I use? This is a good color. Let's suppose that D was 1. D was 1. D was 1. Okay. D was 1. When CLK was 1. So this one will reach the output here. This output is connected to the D input of second slave latch. So this also becomes 1. But since control input of slave latch is 0, this one cannot propagate to the output and it stays there. Okay. Now whatever the output was, it will stay there, it will not change. This one cannot go to the output of the slave latch. Alright. Now let's consider what happens when we get to this point. When CLK goes from 1 to 0. When CLK goes from 1 to 0, this becomes 0. Okay. The control input of master latch becomes 0, which means that master latch is now disabled. But the control input of slave latch goes from 0 to 1. It goes from 0 to 1. Okay. Which means that slave latch is now enabled, and this 1 at the D input of slave latch will propagate to the output. Okay. And for as long as CLK is 0, the control input of master latch will be 0, which means master latch will be disabled, and the control input of slave latch will be 1, which means the slave latch will be enabled, and we will have the output D input going to the output of this flip-flop on the falling edge. This falling edge is where the output changes. Which color should I use? I have not a very big choice. Okay, this is the falling edge. This is the falling edge where transition takes place. Falling edge or negative edge. It's also called negative edge. So that's why this flip-flop, the thing in the red box, it's called negative or falling edge triggered D flip-flop. And actually I'm just going to write flip-flop as FF, flip-flop, D flip-flop. So it's negative edge triggered or falling edge triggered. Negative edge triggered is more common. So negative edge triggered flip-flop. Okay. Now let's draw the truth table of this negative edge triggered flip-flop. The truth table is truth table, सच्चाई की मेज. We have D input, we have CLK input, and then we have Q output and Q bar output. Okay, so these are our inputs and outputs. Okay, when CLK is 0, when CLK is 0, when CLK is 0, it doesn't matter what the value of D is, Q will be last Q and this will be last Q bar. When CLK is 1, it doesn't matter what D input is, it doesn't matter what D input is, whatever we had at Q will remain there and whatever we had at Q bar will remain there. Okay? Alright. Now, when we have falling edge of clock, this falling edge or negative edge of clock, if D is 0, Q will become 0 and Q bar will become 1. And again on falling edge or negative edge, if D is 1, then Q will become 1 and Q bar will become 0. Okay. So the circuit symbol of this flip-flop is like this. We have a D input. Here we have CLK. Here we have Q. And here we have inverted output. Now see this small bubble indicates that it's a negative edge triggered flip-flop. Negative edge triggered flip-flop. Okay. And this small triangle that you see here, it's an indicator that this is clock input. In class I made a mistake. I did not draw this small bubble outside the box adjacent to the clock input. That was a mistake. If I don't have a bubble here, then it would mean that it's a positive edge triggered flip-flop. But in this case, this one is a negative edge triggered flip-flop. It's not a positive edge triggered flip-flop. Alright. So now we want to do one more thing. We want to have an enable input in this flip-flop. Just like we had a control input in the latch when the control input was 0, there was no change in the state of the latch and the output of the latch, but when control input was 1, the D input propagated to output. So likewise, we would like to have an enable input in our flip-flop. We would like to have an enable input in our flip-flop FF. Okay, so let's draw the circuit of that flip-flop. Actually, it turns out it's not very difficult, it's quite easy. So let's see. In this particular case, we only need one latch, one D latch with control input. So this is control input, this is D input, this is Q output, and this is inverted Q output. Okay. Now what we want to do is we want to have a circuit which will not let the output change when enable input is 0. So we want, let's write here what we want. We want to freeze the output when the enable input is 0 when the enable input is 0. Okay, that's what we want. So let's we want to freeze the output when the enable input is 0. So it means we have to somehow feed back the output to the input when enable is 0, and we have to route the D input to output when enable is 1, and we want to do this on the falling edge of the clock. Okay, so let's draw this circuit. So here we have an OR gate, and the output of the OR gate goes in here. Then we have two AND gates, one and two AND gates. The first AND gate is the D input, and the second AND gate, actually, by the way, let me erase this stuff. Let me redraw the figure. There we go. This is our latch. This is the control input. This is the D input of the latch. This is Q of the latch, and this is again Q. Okay. At the input we have an OR gate, and then we have AND gate, and again we have another AND gate, another AND gate, and this is the D input of the flip-flop. Here we have enable input. This is enable input, let's call it en, and this same enable input goes through an inverter or NOT gate into the lower AND gate, and then we have this what you call clock signal. It goes into the control input CLK, and now from here we bring the output of our flip-flop back into the lower AND gate. So this is our normal output Q, and this is our negative output. Let's call it Q bar. Okay, now let's enclose the whole thing into a box. Let's enclose the whole thing into a box, and now we talk about it. Okay, so when enable input is 1, when this enable input is 1, this output will be D, and whatever we have here. Okay, by the way, when this enable input is 1, this input becomes 1 and this input becomes 0. It means this output becomes 0. Okay, so this D comes here, whatever the value of D, it comes here. Here we have 0, so 0 or D is D, and this D is presented to the input of the latch. Okay, so when the falling edge comes, this D is latched to the output. Okay, it is latched to the output. Okay, but when enable input is 0, let's see, when enable input is 0, then this input becomes 1, this becomes 0, this becomes 0, and look, this Q output, it is going all the way back to the input of this AND gate. So 1 and Q is Q. Let's actually, it's better if I erase it. Yeah, that's better. Oops, no, I don't want to do that. Okay. So here the output is Q, this Q comes here, and since this is 0, we get Q here, so Q goes into the input D, and on the falling edge of this CLK signal, the same Q goes to the output again. So you can see that when enable is 1, when enable is 1, D goes to the output. Okay, but when enable is 0, Q goes to the output. Okay, Q goes to the output. So it means that whenever enable is 0, there will be no change in the output of this flip-flop. But when enable input is 1, whatever is the value of D, it will propagate or it will be latched to the output when clock goes from 1 to 0 or on the negative edge of the clock. By the way, for negative edge of for negative edge triggered flip flop, we needed a NOT gate here, and I am sorry that I did not draw the NAND gate, and I am actually going to draw this NAND gate here. I'm going to draw the NAND gate here because I need a NOT gate, sorry, not NAND but NOT. I need a NOT gate here because I want this to be a negative edge triggered D-type flip-flop with enable input. Okay. So when clock goes from high to low, it latches to the input latches to the output, assuming that En is 1. Okay. So the circuit symbol of this flip-flop, let's draw it here because I've run out of space on this page and I don't want to start a new page. So this is our flip-flop. This is the dynamic clock indicator, and this is bubble indicator. It's a negative edge triggered flip-flop. And then we have enable input En. We have D input D. We have Q output, and then we have negative Q output. Okay. So this is the circuit symbol of a negative edge triggered D-type flip-flop with enable input. Alright, so does it make sense? So with this we complete our discussion of latches and flip-flops, and I can actually tell you that there is a TTL logic family chip. I think it's 74X74. It's a flip-flop. Let me quickly check on my Google TTL flip-flop. D-type. Let's see. Yeah, it is 74X74. 74X74. So this is correct. It's a flip-flop, TTL flip-flop. Now I don't know whether it's positive edge triggered or negative edge triggered. I think it's positive edge triggered D-type flip-flop. And actually the IC contains 2 flip-flops, not 1. It contains 2 flip-flops. So there are other ICs which have more than 2 flip-flops, but you get the general idea that this is an MSI device, which is SSI, I think we can call it SSI device, small scale integration device, and you can use it in your designs. Now let me just tell you that there are JK flip-flops, then there is a T flip-flop, and is there any other type of flip-flop? Okay, this J and JK and T I can, yeah, there is an SR flip flop as well. SR flip flop, SR flip flop. Yeah, there is an SR flip flop, and so basically JK flip flop, SR flip flop, SR flip flop, JK flip flop, T flip flop. But almost all of the designs these days, they are based on D flip flop. Most common. That's right, most common. Most common. Okay. All right. So with this, we conclude our discussion of latches and flip flops, and the next thing that we want to discuss is registers and MIPS register files. Okay, so I am going to stop now, and then we will upload the thing. Okay, there we go.